Welcome to Room 3, Physics. I would like to talk about a few problems that we covered this year. One of the problems we covered way back was a conversion problem that had to do with this idea of the Jiffy. Now the Jiffy was defined as a new time unit, and it has been defined in many different ways. The way that we defined it was the time it takes light to travel 1 centimeter. And what is that in seconds? Well, we started with a basic formula for speed. Speed equals distance over time. And for speed, I use the symbol v. We use that quite a bit in physics. Usually refers to velocity, but in this case, we're using it for speed. And I use d for distance and t for time. And I know what the distance is in this formula. It's 1 centimeter. I need to convert it to meters to stay in SI units. I also know what the speed is. It's the speed of light. And I'm going to use the speed of light in free space, and I'm going to round it to one significant digit. I'm going to use the number 3 times 10 to the 8th meters per second. And I'm going to convert centimeters to meters by dividing by 100. I move the decimal 2 to the left, so it becomes 0.01 meters. And I solve this formula for the time. That'll give me the amount of seconds in a jiffy. So let's do that. Over here, I'll rewrite my formula. Time equals distance divided by speed. Distance divided by speed. In fact, if you take any distance and you divide it by the speed that you're going, let's assume your speed stays constant, you can figure out the time of travel. So let's plug in our numbers. What's the distance? It's 0.01 meters. 0.01 meters. That's 1 centimeter. And it's divided by the speed of light. The symbol we usually use for the speed of light is c. But I'm going to write it in scientific notation, 3 times 10 to the 8th meters per second. And then when I look at this math problem, that's all it is now, is a division problem. The units cancel out. Meters cancels out meters here, and the seconds come upstairs. And when you work this out, it comes out to be approximately 3 times 10 to the negative 11 seconds. That's how many seconds makes up 1 jiffy. That's a very small number. Because light is has a very, very fast speed. It's going to cover this tiny distance just like that. Now, the other question we dealt with was a conversion problem. How many jiffies are in a minute? Well, we can use this as our conversion factor. This is telling us that 1 jiffy equals 3 times 10 to the negative 11 seconds. That's conversion factor. We could write it two different ways. We could write it jiffies per second or seconds per jiffy. I'm going to write it as jiffies per second. And then I'm going to convert the seconds to minutes. And then I'll have jiffies per minute. So here's how I do it. I'm going to take the reciprocal of this number. It's going to look like this. Jiffy, 1 jiffy, per 3 times 10 to the negative 11 seconds. And now I just want to convert seconds in the denominator here to minutes. And the way I do that is I'm going to have seconds upstairs to cancel out seconds downstairs here. And I'll put minutes on the bottom. Then I'll have jiffies per minute. So how many seconds make up a minute? 60 seconds per 1 minute. The units cancel out here. Seconds cancels out with seconds. Now jiffies per minute. So I'm going to divide 60 by 3 times 10 to the negative 11. What happens here is I get 2 times 10 to the 12th. And that's jiffies, that many jiffies per minute. And that's a very large number, which makes sense. So there you go. That's really a simple conversion problem. We had one definition. The jiffy was defined as the time it takes light to travel 1 centimeter. We converted centimeters into meters by moving the decimal over 2 to the left or dividing by 100. Recall that 100 centimeters equals 1 meter. We used the speed of light here in free space to one significant digit, 3 times 10 to the 8th meters per second. We used the simple formula here for speed. Speed equals distance over time. We solved that for the time. So time equals distance over speed. Once we did the math here and figured out how many seconds make up a jiffy, We use that as conversion factor to figure out the second question. The second part question was, how many Jiffies are in a minute? In a simple conversion problem. Thank you. Welcome back. I'd like to talk about an additional problem we covered. It has to do with a bowling ball and an ant walking along the surface of this bowling ball. Here's the bowling ball. The ant is at the top. This bowling ball has a certain radius, and it's going to walk along the surface here. And I'm interested in the point at which the normal force equals 1/2 the ant's weight. When that occurs, the ant begins to slip. So let's figure out what the angle is that the ant cuts out as it walks along this bowling ball. What is this angle when the normal force on the ant is equal to 1/2 its weight? Let's solve that. I'm interested in this point. So what is the normal force? Well, the normal force is always perpendicular to the surface, and it'll point away from the ant, like that. And the weight of the ant will point directly down towards the center of the earth. That's the weight, mg. I need to analyze these forces. This is a semi-free body diagram. Let's put it in a coordinate system. I like to put as many vectors as I can on one of the axes. I'm going to put the normal force on the y-axis, and I'm going to draw a tangent line, dotted line, through where the ant is at that point. I'm going to call that the x-axis. And this is perpendicular to that tangent line, since it's the normal force. Now the weight is a vector, and it can be decomposed into an x and y component. And what you do is you start with the point right at the tip of the vector, and you drop a perpendicular down to the x-axis and a perpendicular down to the y-axis, which continues below the ant here, or on this side. And this distance from the ant to where you hit the axis here, this would be called the x component of the weight. And this right here, from the ant to where you hit the y-axis, this would be called the y component of the weight. And the only other thing we need is to relate this angle to these two right triangles that we've created in this picture here. So if I redraw this picture, what I have is I have the normal force this way. This is more of a traditional free body diagram now. I have the weight straight down. I made my axes, x and y. It's a tilted coordinate system. I have my component, my x component. This is mg. And I have my y component. I decompose this vector into its components. Now these are right triangles here, but I need to know where theta is in relation to these triangles. One way to look at it is if you look at the vector that represents the weight, it's parallel to the radius here. And the y-axis cuts across those two parallel lines, and that y-axis would be called a transversal. And in geometry, you should have learned that this angle here equals or is congruent to this angle. They're equal in measure, because alternate interior angles are congruent. Also, in this right triangle, this angle will correspond to this angle, and they'll be congruent. And that helps us to figure out what the components are. If I wanted to know what the x component was in terms of the weight, it would be equal to the hypotenuse side, mg, times the sine of that angle because it's across from it. You should recall how we did that using basic right triangle trigonometry. And the y component, little typo here, let me change it to y. I'll be careful with this. The y component will equal the magnitude of the weight. I'll write it down here, which is mg. Now times the sine of theta, it's adjacent to the angle, it'll be the cosine of theta. And that's something you should know right off the bat. Remember, the sine and cosine give you a fraction of the total weight. The weight's being broken up. And remember, this is the hypotenuse of a right triangle. It is the largest side. The legs will be reduced. And you get this reduced amount from either the sine of theta or the cosine of theta times the total weight. You get a fraction of the total weight. Okay, now how do we solve this problem? Well, we're interested in finding this angle. But we want to use Newton's second law of motion to solve for this. And I'm interested in the y direction. This y direction here, these two forces are equal and opposite. It's not accelerating one way or the other. So I know the net force is 0. No acceleration, net force is 0. So when I apply F equals ma, I'm going to make this side 0. The sum of all the forces, the net force, will equal 0. And I could write it with summation notation. The sum of all the forces equals 0 like that. And what are the sum of the forces? Well, it's going to be the normal force minus the weight. But it's the y component of the weight. This force minus this force. And up is positive. It's the positive direction. So I'm going to have the normal force, its magnitude, minus the y component of the weight. I'm going to set that to 0 because it's not accelerating. And that means the normal force will equal the y component of the weight. And what is the y component of the weight? Well, we figured it out right here. It's mg cosine theta. And what is the normal force? Well, in our condition, we're assuming the ant will begin to slip when the normal force is 1/2 the weight of the ant. So let's put in for the normal force. Let's substitute in that assumption. The normal force equals 1/2 the weight of the ant, which will be mg. The ant's mass will be just m. Its weight will be m times g. So let's substitute n equals 1/2 mg on this side. 1/2 mg. If we do that, we can clearly see what's going to happen here. Mg, the weight on both sides, is going to cancel out, and we're going to need to figure out what the inverse cosine of 1/2 is. Now you should know the cosine of what angle, what particular angle gives you 1/2. You should already know that. And if you don't know that, you can actually use your calculator or look it up in a table and take the inverse cosine of 1/2. When you do that, and you want to be in degree mode, take the inverse cosine of 1/2, you should get 60 degrees. Because the cosine of 60 degrees is 0.5 or 1/2. So, if this is the condition for slipping for the ant, 1/2 its weight, the normal force being 1/2 its weight, then the angle is going to work out to be 60 degrees. Once that ant has traveled that particular amount of angular distance, it will begin to slip. And if it doesn't have sticky feet or something else to hold it on to the bowling ball, it will begin to fall off. Thank you. Welcome back. I wanted to talk about an additional problem that we covered this year, and it was called the Atwood's machine. The Atwood machine is a nice little device. It's made out of a simple pulley. Actually, it's an ideal pulley. And it has a cord going around it. And there's masses on the ends of this cord. And one of the masses I could call M1. The other mass I could call M2. It's going to move this way. It's going to accelerate up on this side and down on that side. So accelerate up on this side and accelerate down on this side. And we're making this the positive x direction, say. And the question is what is the acceleration of this system? And also, what is the tension in the rope or cord that's wrapped around the pulley? So let's go about and review this once again. This is a connected objects problem, and you can analyze it using Newton's laws of motion separately for each object. We are ignoring the pulley in this case because it's an ideal pulley. There are a few assumptions we're making. But let's just review what we've talked about. Let's solve the equation of motion, Newton's second law, for mass 1, and then solve it for mass 2, and combine the results. So for mass 1, we draw a free body diagram. Remember, a free body diagram, we're just showing the mass as a point particle, and we're drawing in all the forces acting on that we're interested in. We're interested in its weight, which is the force of gravity pulling on it, and it pulls straight down, and near the surface of the Earth, it's equal to its mass times the acceleration of gravity. And the acceleration of gravity is considered constant near the surface of the Earth, and we're going to use 9.81 meters per second squared for that. And also what's acting on here is the tension in the rope. The tension is up. So the weight down, the tension up. And if this is accelerating upward, as it is on this side, is accelerating upward, then the tension here, which is a force, is greater than the weight. That's why it's accelerating upward. There's a net unbalanced force. Let's apply F equals ma to this. If I apply F equals ma, well, what is the net force? Well, the tensions must be greater than the weight. I put the tension first, and I would subtract the weight. The difference between those two is the net force. The net unbalanced force produces the acceleration on this particular mass, which is m1. So let me write that in. m1, and there's the acceleration. Now that's one useful equation, and I'm going to just call that equation 1. I need another equation though. And I get the other equation from the second mass. These are connected objects that have the same acceleration. The only difference is this one is accelerating up, and this one's accelerating down. So let's do m2. So for the free body diagram for m2, it looks similar. You have the weight down towards the center of the earth, m2g, and the tension is still up. But it's accelerating downward. This is the heavier mass, the heavier weight. It's accelerating this way, so it means the weight, m2g, is greater than the tension. So I'm going to write the formula this way this time, for F equals ma. The net force is the weight minus the tension. The difference between those two is the net force, the net unbalanced force, which produces the acceleration on the second mass here. These accelerations are the same because they're connected objects. And that's our assumption. Number 1, number 2. If we combine these two equations, we can eliminate the tensions. And then we can solve or come up with a formula to solve for the acceleration just based on the masses alone. So let's do that. I'm going to line these up. I'm going to bring equation 2 and put it under equation 1. Just to line these up. And now I have two equations, my second equations. Two equations, two unknowns, acceleration and tension. Those are the two unknowns I'm interested in. I'm assuming I know what the masses are. And what I'm going to do is I'm going to add these equations together, and through the process of elimination, I'm going to get rid of one of the variables. And the one I'm going to get rid of is the tension right away. I have plus t here and minus t here. These terms will cancel out, and what I'll be left with is m2g minus m1g on the left side. On the right side, I'll have m1, m2, I could write it that way, m1 plus m2, and that quantity is times a. I just factor the a out because it's in common. And I could also factor the g out on this side and solve this for a. And when I do that, what I'll get is a equals m2 minus m1 times g on the top there. m2 minus m1. That whole thing's times g on the top. And on the bottom, I'm going to get m1 plus m2. And I'll write it that way. Or I can write it m2 plus m1. But it is a sum. So notice on the top I got the difference between the two masses. And on the bottom I have the sum. And that is a fraction of g. Let me write this up here. The acceleration in this Atwood's machine will equal a fraction of g. And that fraction is given by the difference in the masses, the larger mass first, minus the smaller mass. And then you sum the masses, m2 plus m1, and multiply by g. This is a useful formula for figuring out the acceleration in this particular device. You could also go back and plug this acceleration into one of these formulas and solve for the tension. And there's a nice formula for tension that we used that's very useful as well. But this was one of the key results that we studied here. Thank you. Okay, let's continue with this problem. I want to solve for the tension now. The results I have up here on the board is the acceleration for the Atwood machine is a fraction of g. And I want to take this and plug it into one of these equations. I think I'm going to use equation 1. So let me erase this picture here. I'm going to take equation 1, which is T minus M1G equals M1A. And I'm going to substitute my expression for A for the Atwood machine I have over here. I'm going to substitute it in here for A and then solve for T. And I'll get a nice equation I can use for the tension in the Atwood machine. So let's do that. T minus M1G equals M1. Plug that in. I have M2 minus M1 over M2 plus M1 times G. Now I need to do just some algebraic manipulation here to solve for T. I can simply add this to both sides. So if I add this to both sides, it cancels out on this side, it goes to 0. And on this side I have this term, M1 times M2 minus M1, M2 plus M1, G plus M1G. This is a nice expression for the tension. I could use that. However, I could simplify this. So let's go about simplifying that. I'm going to erase my Newton's law derivations here. So let's see if we can't simplify this, and I'll erase this as well. So let's take this up here and try to simplify it. Well, what can I do there? Well, I could factor out M1G. I could do that, so let's do that. Tension equals, I'm going to factor out these two terms here. Let's see what happens. M1G, I factor that out. And what's left behind? Well, my first term, I have this fractional part. M2 minus M1 over M2 plus M1. And then I have plus 1. And in these parentheses here, I have this fraction plus, 1 over 1, this is a fraction 2. Let's combine these but with a lowest common denominator, which would be M2, M1. So I'm going to multiply top and bottom here by, M2 plus M1. M2 plus M1. And what's going to happen there? Well, I'll be able to combine everything under M2 plus M1. Remember, when you add fractions, you need a lowest common denominator. So there it is, M2 plus M1 or M1 plus M2, doesn't matter which way you write it. And on top, what do I have? Well, I have M2 minus M1 here plus M2 plus M1. I could put these in parentheses just to show you there are quantities. But since it's all addition and subtraction here, I can drop the parentheses and just cancel out what cancels out here. And if you look at the top part here, well, what cancels out? Well, I have M2 plus M2, that's 2M2. But minus M1 plus M1, well, the M1s are going to cancel out. So they're gone. I'm just going to have M2 plus M2, which is 2M2. Add like terms. So I'm going to have M1G times 2M2. So I can pull a 2 out here. I can put M1 there. Remember, M2 plus M2, that's where the 2 came from, 2M2. 2M2, there it is. 2M2 times M1 times G. And G will be up here. I just want to look at that part. I'm going to separate the G out. And what's underneath? M2 plus M1. The sum. And there we go. Let's write that again. The tension simply equals the fraction here of 2M1 times M2 over M1 plus M2. I'll switch those around. It's easier to say. And that's multiplied by G. So just like the acceleration was a fraction of G, the tension is a fraction of G. And this is a nice, useful formula. And recall the acceleration, it came out to be the difference between M2 and M1, M2 minus M1, over the sum of those two. And you could write it M1 plus M2 or M2 plus M1. I like to write it M2 plus M1 sometimes. And then there's G. And this is the acceleration for the Atwood device, and that's the tension for the Atwood device. Thank you. Welcome back. I wanted to continue on with the Atwood machine, the Atwood device, and there was a problem we did in class that had to do with an Atwood machine where one side was 110 newtons and the other side was 63 newtons. So I'm going to make this side the 110 newtons and I'll make this side the 63 newtons. Now that's how much these particular masses weigh, mass times gravity, the acceleration of gravity. These are weights, and I want to figure out what the acceleration is. That's one thing, but better yet, I want to figure out what the tension is in the cord or rope there. So how do we find the tension? Last time I derived a formula for the tension, and if you recall, the tension was a fraction of g. And that fraction was 2 times m1 times m2 divided by m1 plus m2. You would multiply that by g. Now you could use this formula directly to get the tension if you converted the weights into mass. But you could also rewrite this formula if you'd like to convert this formula into a formula that uses weights. So why don't we do that? Let's take this formula and convert it. And how would that look? Well, you could start off by writing the formula down, and instead of writing, m1, you could write it in terms of weight. And you should remember that weight equals mass times the acceleration of gravity near the surface of the Earth. So let's solve that for mass. Mass will equal the weight divided by the acceleration due to gravity. And for m1, it would be w1 over g. For m2, it would be w2 over g. Well, let's do that. Let's put 2 times w1 over g for m1 times w2 over g for m2. And that's going to be divided by, you can do the same thing here, w1 over g plus w2 over g. And of course, up here there's another g. Now if we simplify that, notice that we have a fraction underneath here that needs to be combined with the g's here. We could put that over g. And let's do that. Let's look at the bottom first. I'm going to put that over g. Most common denominator is g, and that would be w1 plus w2. Remember, there's a g right there. Now what happens up here at the top? I have 2w1, w2 divided by what? Isn't that g times g? That would be g squared. So I have 2w1 times w2 over g times g, that's g squared. So what happens to all these g's? Any idea? Well, if I do this part, this is a fraction divided by a fraction. If you remember, to divide fractions, you invert and multiply. So if I was to write this out so you could see it, which you don't have to do in this case, but it's multiplying by this, but it's reciprocal. Invert and multiply, divide, invert and multiply. That's what it means. So I put g up here, and I put w1 plus w2 down there. And remember, there is another g outside here. But notice this, g times g is g squared. G squared on top, g squared on bottom, they will cancel each other out. And you will be left with, for the tension, simply 2 weight 1 times weight 2 over weight 1 plus weight 2. And this is a nice formula to use in terms of weight. And notice there's no g in the equation. This one has g when you do it in terms of mass. But if you want to do it in terms of weight, just replace the m's with w's, or flip them. The m flip becomes a w, and take away the g. So if we want to solve this problem now, assuming it's accelerating, we want to figure out what the tension is. Let's use that formula. We plug it in. The tension will equal 2 times weight 1. We call this weight 1. Call this one weight 2. So 63 newtons times 110 newtons divided by 63 newtons plus 110 newtons. When you do the calculation, it comes out to be approximately 80 newtons. And it should be somewhere between 63 and 110, because if you remember from our previous discussions, this side, which is accelerating upward, the lighter side is accelerating upward, the heavier side is accelerating downward. The side that's accelerating upward gains weight, apparent weight. The apparent weight is measured by the tension, which becomes 80 newtons. So this goes from 63 to 80 newtons. The other side loses weight. It goes from 110 newtons to 80 newtons. The tension is the apparent weight, or by definition, the weight. So one side gains weight, the other side loses weight, but they both weigh the same, which is the tension of 80 newtons.